Hello students, this is lecture 15 of MTH 201. In the last lecture, we discussed equality of mixed partial derivatives, second order Taylor's formula for a function of two variables near a given point, and we also obtained from the Taylor's formula the linear and quadratic approximations of the function near a given point. So today we are going to talk about what are called extrema of a function. So you already know of this concept for a function of one variable where you talk about local maxima, local minima, absolute maxima and absolute minima. So today we are going to extend these ideas to a function of two variables. Okay. So here in this picture you have graph of a function of two variables, and there are several peaks as you see in the graph. There are precisely four peaks, 1, 2, 3 and 4. So by local we will mean some feature that is happening in a local neighborhood, local region about that point. So if you look at this point, locally it's a maximum, right? If you compare the value of the function at this point, it's bigger than all the values that happen in a local piece, right? Similarly, here also you have that feature. It's a local maxima, right? Now, here it's again a local thing, but it's a minimum, right? It takes minimum value. And then this is also a local minimum. But among all these four, there is one absolute maximum, which is this, where the value is larger than all the other values possible of the function. And here, the value is minimum, is smaller than all the values possible of the function in the entire domain. Okay. So let us make these concepts precise. So let fxy be a function of two variables. Let us first define a local minimum point or a local minima of this function. So a point x0, y0 is said to be a local minimum point for f if there is a disk about x0, y0 such that fxy is greater than or equal to fx0, y0 for all x, y in the disk. Meaning in a disk about this point, the function takes values which are bigger than or equal to this given point. Then you say that this point is a local minimum point. Okay, so this feature is happening locally. Similarly, you can define local maximum point or local maxima, and you say that a point x0, y0 is a local maximum point for f if there is a disk about x0, y0 such that fxy is less than or equal to fx0, y0 for all x, y in the disk, which means that f takes values smaller than the values of the function at the given point. Then you say it's a local maximum point. Now, we can club these two notions and we have a concept of local extremum or local extrema. So a point that is either a local maximum or a local minimum is called a local extremum. Okay, so that it encompasses these two notions. This was about local, right? Now, what about absolute? So absolute minimum point or absolute minima is defined as follows. So suppose D is the domain of f. So D is the set in R2 where this function f is defined. That f has an absolute minimum at this given point in the domain if the value of the function at this point is smaller than all the other possible values in the domain, in the entire domain. Now it's no longer a local feature, it's a global feature. It's happening everywhere on the domain. Similarly, you have absolute maximum point or absolute maxima. So f has an absolute maximum at this given point if The value of the function at this point is bigger than all the other possible values of f in the entire domain. Okay, so the picture is a good representation of these definitions. Okay. Now let us talk about a critical point. So this notion is again something that you have seen for functions of one variable. So let us extend that idea to a function of two variables. So let fxy be a function of two variables. A point x0, y0 is called a critical point of f if either of the two things happen. Either the gradient of f at this point is not defined, in which case we can't talk about the tangent plane, right, at that point. Or the gradient of f at this point is nothing but the zero vector. Okay. So if f is differentiable at this point, then what is the equation of the tangent plane to the graph of the function at this point? It's nothing but z equal to fx0 y0, because the other two terms which were corresponding to the partial with respect to x at the point x0 y0 and partial with respect to y at the point x0 y0 are both 0, right? Because the gradient is 0. Function is differentiable. So gradient exists, right? And it is 0. So therefore, this is the equation of the tangent plane. This means this is like z equal to constant, right? Now, z equal to constant means that the tangent plane is horizontal at that point, right? And the normal is nothing but k. So in this picture, you can see that at all the four peaks, right? Peaks on the top and also peaks on the bottom. When you draw the tangent plane, they will all be horizontal. So that is what happens at critical points. Okay. So now let us see how to find out extreme points, right? So this is a very famous test, and you have also seen this in MTH 101 for one variable function. Now we have a function of two variables. So let fxy be a differentiable function. Remember, it's a function of two variables. If x0, y0 is a local extremum of f, then x0, y0 is a critical point. That is, the gradient of the function has to be 0, or it's the 0 vector. So extrema implies critical point. So the proof is, will take you back to MTH 101. So first of all, assume that this given point x0, y0 is a local maximum point. So whatever steps we do for local maximum, similar steps can be followed to prove the statement when x0, y0 is a local minimum point. Okay. So what is the procedure? You define a new function gx, which is f of x comma y0. So you can think of this as you're fixing y, right? So when you fix y, that means you are in the xy plane, you are walking along the horizontal line, right? Y equal to 1. So your x is varying, so now you have a function of one variable, right? Now what is the derivative of g with respect to x? It's nothing but the partial of f with respect to x at the point x comma y0, right? Because the second coordinate is independent of x. Therefore, if you evaluate it at x equal to x0, then g prime x0 is fx x0 y0, right? So the derivative of g at x0 is nothing but the partial derivative of f with respect to x at the point x0 y0. Now, if you look at gx, which is f of x comma y0, now remember x0 y0 is a local maximum point. Therefore, this value is less than or equal to f of x naught y naught in some disk about x naught y naught, right? But f of x naught y naught is nothing but gx naught, right? So therefore, gx is less than or equal to gx naught for all x in some disk about x naught. But what does that mean? That means that x naught is a local maximum point for g, right? Because that is the definition of local maximum in one variable, right? That the function takes the value largest in some disk about that point, right? So now from first derivative test from MTH101, you know that the derivative of g at this point has to be 0, right? Because it's a local maximum. But we just computed g prime xy x naught. What is g prime x naught? It's fx x naught y naught. So therefore fx x naught y naught is 0. So what did we do in this proof? We went back to one variable. We constructed a function which is a function of one variable, and we figured out that the partial, one of the partials is 0. Now to prove that fy, which is the partial with respect to y of f at the given point is 0, you define another function where you fix x coordinate x naught and you vary y, and you follow similar steps. So I'll not go into the details, but you can have a look. So this function will give you that fy, the partial of f with respect to y at x naught y naught is 0, and therefore both the partials are 0 and therefore gradient is 0, right? So it is a critical point. And you can do the similar steps, you can follow similar steps when x naught y naught is a local minimum point instead of a local maximum point. The difference would be that this inequality will be reversed. This will become minimum. Similarly, this inequality will be reversed and this will become minimum. Okay, and then everything else will be similar. So what have we done now? So we know that if a point is a local extremum, then it has to be a critical point, right? So using the first derivative test, if we have to find extremum points, we find critical points, right? Because at any extremum point, your gradient has to be 0. It has to be a critical point, right? So therefore, critical points is a bigger set than extremum points, right? Local extremum points. However, not all critical points are local extremum. So let us look at this example. So if fxy is x square minus y square, you compute the first derivatives of f. When you set them both equal to 0, you get x equal to y equal to 0. This means that 0, 0 is the only critical point of f. What are critical points of f for a differentiable function? They are nothing but points where gradient is 0. For this particular example, gradient is 0 at only 0, 0, right? Now the question is it a local extrema? Okay. So now let us see. At 0, 0 value is 0, right, of the function. So we have to see around 0, 0 what's happening. Now, if you set y equal to 0, that means if you are on the x-axis, then the function value is x square, which is always positive when x is non-zero, right? So at 0, 0 value is 0. On the x-axis value is positive, and on the y-axis, meaning when x is 0, value is negative, right? So therefore, there is no disk about 0, 0 where the value at 0, 0 is either the largest or the smallest, right? So therefore there is no disk about 0, 0 in which f00, which is 0, is the minimum value or it is the maximum value. And hence it is not an extremum, right? Because extremum means, local extremum means that either it is a local maxima or it's a local minima. And such a critical point is called a saddle point. So let us look at this picture, saddle, the literal term of saddle here. So if you look at the graph of this x square minus y square function, what's happening is you see that this is the point 0, 0, value is 0, right? Along the x-axis value is positive, right? And if you walk, which is the, so x-axis is red axis here and y-axis is green axis here. And along the y-axis values are negative, right? So what's happening is you have along these curves 0, 0 is minimum, and along these curves which are parallel to this axis you have maximum, right? So you don't have uh, 0, 0 as a local extrema, right? And such points are called saddle points. It's like horse saddle, right? The same shape. Okay, let us look at a few examples. So let us find all the critical points of this function. It's easy, you compute the first derivatives, first partial derivatives, set them equal to 0. In this particular case, this implies that x and y are both 0, therefore 0, 0 is the only critical point of f. Now the question is it a local extrema? And that's a hard question in general. In general, it's very difficult to decide whether a point is a local extremum or not. Okay. Let us look at another example. Find all the critical points of this function. Again, you compute first order partial derivatives, set them both equal to 0. In this particular case, you will get x to be 9/5 and y to be negative 6/5. Therefore, this is the only critical point of f. Now, the question is it a local extremum? Again, we can't say directly. In general, it's not easy to check whether a point is a local maximum, local minimum or a saddle point. Thus, we need more tests. And one of the famous tests is second derivative test. Okay. So, we've seen second derivative test even in MTH 101. Now, we will generalize it. Okay. So let fxy be a C1 function. What is a C1 function? A function which is differentiable and whose second order partial derivatives are continuous. Suppose you are given a critical point of f. Okay. So that means the gradient of f at this point is 0 because the function is differentiable. You construct this matrix H at this point, which is a 2 by 2 matrix consisting of second order partial derivatives of f at this point. So the diagonal terms are fxx, fyy, and the off diagonal terms are mixed partials. Now this is a symmetric matrix. Why? Because the second order partial derivatives are continuous, therefore fxy is equal to fyx, right? So it's a symmetric matrix. And this matrix is known as the Hessian matrix of the function at the given point. Now you define capital D to be D of x naught y naught, which is nothing but the determinant of this matrix. So remember, we are doing all this at the critical point, right? So this is the determinant of this matrix, and the second derivative test tells us the following. So if this determinant is positive and fxx at the given point is positive, then f has a local minimum at this given point. If the determinant is positive and fxx is negative, then you have a local maximum at this point. If the determinant is negative, then this point is a saddle point. That is, f does not have a local extremum at the given point. Okay? And finally, if the determinant is 0, then the test doesn't give you anything. This test is inconclusive. The point x0, y0 could be anything. It could either be a local maximum, local minimum, or a saddle point. We don't know. Okay? Fine. So let me talk about a few things here. Now you might be wondering why we took fxx and not something else. So note that if d is positive, which means this is positive, then the first term has to be positive, right? Because if first term is negative, then everything is negative. So for this to be positive, the first term has to be positive. So that means fxx and fyy have same signs, right? For the product to be positive. Therefore, it doesn't matter whether we write this condition in terms of fxx or fyy. It's the same thing. Similarly for the second term, right? Because d is positive, they have to have same signs. So if fx is negative, then fyy also has to be negative, right? And in the third scenario, when d is negative, then anything can happen. So we don't need that much. So this becomes a saddle point. So why does it work? So you will see an exercise in problem set for this week where there will be some sort of justification for why second derivative test works. Okay, so I'll defer this to the problem set. But this is the second derivative test. Now let us revisit this old example that we saw a few minutes back. So here we computed that 9/5 minus 6/5 was the only critical point. So let us now apply second derivative test to check the nature of this extremum. So here you can easily compute that these are the values of second partial derivatives which actually do not depend on the critical point here. And if you compute, I'm sorry, this should not be 0, 0, this should be 9/5 minus 6/5. So if you compute the determinant of the Hessian matrix at this point, it comes out to be negative and therefore this has to be a saddle point, right? This is the picture, this is the graph of the function. It's very much like x square minus y square. You can see that you have uh, at this critical point in one direction it's a maxima, in other direction it's a minimum. Okay. Let us look at another example which has more features. So you consider this function. These are the first partial derivatives. When you set them equal to 0, you get 3 critical points, which are these. Now, let us apply second derivative test. For second derivative test, you need to compute all the second order partial derivatives. And you can check that if y is 0, then fxy is 0, right? And y is 0 in all these 3 points. So we don't even have this term. So the Hessian matrix in all the 3 cases is a diagonal matrix. So when you compute the determinant at the point minus 1, 0, it comes out to be negative, therefore it's a saddle point. At 0, 0, it comes out to be positive and fxx is negative, so it's a local maxima. And at 2, 0, the determinant is positive and fxx is positive, so this point is a local minima. So this should not be 0, 0, it should be 2, 0. This is the graph of the function. So this is the x-axis. So there are 3 points, minus 1, 0. So minus 1, 0 is here. So you can see that minus 1, 0 is a saddle, right? In this direction, it's a minimum. In this other direction, it's a maximum, right? Now, at 0, 0, this is the point. You can see that it's a maxima, right? It's bigger than all the possible values in some local disk. Now you come to the point 2 comma 0, 2 comma 0 is here. You can see that it's the minimum value in some local region about this point, right? So this is your local minimum. Okay. So now this is a preamble to the next lecture. So in one variable calculus, you talk about absolute extrema, right? And how do you compute absolute extrema? So suppose you have a function of one variable, y equal to fx, differentiable function. To find absolute minimum or maximum values of f in some closed interval ab, first of all, you find all the critical points of f in this open interval AB by doing what? By solving f prime x equal to 0, right? Then you look at the values of function at all these critical points, let me call them x1 through xn, and also the endpoints. And you compare all these values. The largest value is called the absolute maximum. Smallest value is the absolute minimum, right? And the points where these are attained are called points of absolute maxima or points of absolute minimum, respectively. This was happening in one variable calculus, right? In the next lecture, we will extend this idea to functions of more than one variable. We will introduce a well-known method which is known as Lagrange multiplier method, which is quite popular in optimization theory. Okay, so we will do this in the next